Gravity. Explanation about the topic gravity. Gravity, also called gravitation. In mechanics, the universal force of attraction acting between all matter. It is by far the weakest known force in nature and thus plays no role in determining the internal properties of everyday matter. On the other hand, through its long reach and universal action, it controls the trajectories of bodies in the solar system and elsewhere in the universe, and the structures and evolution of stars, galaxies, and the whole cosmos. On Earth, all bodies have a weight or downward force of gravity proportional to their mass, which Earth's mass exert on them. Gravity is measured by the acceleration that it gives to freely falling objects. At Earth's surface, the acceleration on gravity is about 9.8 meter, 32 feet as per second. Thus, for every second an object is in free fall, its speed increases by about 9.8 meters per second. At the surface of the moon, the acceleration of a freely falling body is about 1.6 meters per second per second. The work of Isaac Newton and Albert Einstein dominate the development of gravitational theory. Newton's classical theory of gravitational force held sway from his Principia published in 1967 until Einstein's work in the early 20th century. Newton's theory is sufficient even today for all but the most precious applications. Sufficient even Einstein's theory of gravitational relativity predicts only minute quantitative differences from the Newtonian theory explains in a few special cases. The major significance of Einstein's theory is its radical conceptual departure from classical theory and its implications from further growth in physical thought. The language took great improvements in measurements of gravity around Earth, other planets and the moon, and in experiments on the nature of gravitation.
Development of gravitational theory early concepts. Newton argued that the movements of celestial bodies and the free fall of objects on Earth are determined by the same force. The classical Greek philosophers, on the other hand, did not consider the celestial bodies to be affected by gravity because the bodies were observed to follow perpetually repeating non-descending trajectories in the sky. Thus, Aristotle considered that each heavenly body followed a particular natural motion unaffected by external cause or agents. Aristotle also believed that massive earthly objects possess a natural tendency to move toward Earth's center. Those Aristotelian concepts prevailed for centuries along with two others, that a body moving at constant speed recovers a continuous force acting on it, and that force must be applied by contact rather than interaction at a distance. These ideas were generally held until the 16th and early 17th centuries. Third part, embedding an understanding of the true principles of motion and precluding the development of ideas about universal gravitation. These impasses began to change with several scientific contributions to the problem of earthly and celestial motion, which in turn set the stage for Newton's later gravitational theory. The 17th century German astronomer Johannes Kepler accepted the argument of Nicholas Copernicus, which goes back to Aristoteles of Samos, that the planets orbit the Sun, not Earth, using the improved measurement of planetary movements made by the Danish astronomer Tycho Brahe during the 16th century. Kepler described the planetary orbits with simple geometric and arithmetic relation. Kepler's three quantitative laws of planetary motion are: the planets describe elliptic orbits of which the Sun occupies one focus. A focus is one set of 2 points inside an ellipse. Any ray coming from one of them bounces off a side of the ellipse and goes through the other focus. The line joining a planet to the Sun sweeps out equal areas in equal terms. The squares of the period of revolution of a planet proportional to the cube of its average distance from the Sun. During this same period, the Italian astronomer and natural philosopher Galileo Galilei made progress in understanding natural motion and simple accelerated motion for earthly objects. He realized that bodies that are uninfluenced by forces continue indefinitely to move, and that force is necessarily to change motion, not to maintain constant motion. In studying how objects fall toward Earth, Galileo discovered that the motion is one of constant acceleration. He demonstrated that the distance a falling body travels from rest in this way varies as the square of the time. As noted above, the acceleration due to gravity at the surface of Earth is about 9.8 meters per second. Galileo was also the first to show by experiment that bodies fall with the same acceleration whatever their composition, the weak principle of equivalence. Newton's law of gravity. Newton discovered the relationship between the motion of the moon and the motion of a body falling freely on Earth. By his dynamical and gravitational theories, he explained Kepler's law and established the modern quantitative science of gravitation. Newton assumed the existence of an attractive force between all massive bodies, one that does not require bodily contact and that acts at a distance by invoking his law of inertia. Bodies not acted upon by force move at constant speed in a straight line. Newton concluded that a force exerted by Earth on the Moon is needed to keep it in a circular motion about Earth rather than moving in a straight line. He realized that this force could be at long range, the same as the force with which Earth pulls objects on its surface downward. When Newton discovered that the acceleration of the moon is 1/3,600 smaller than the acceleration at the surface of Earth, he related the number 3,600 to the square of radius of Earth. He calculated that the circular orbital motion of radius and period T requires a constant inward acceleration A equal to the product of 4 4 2 and the ratio of the radius to the square of the time. The moon's orbit has a radius of about 384,000 km to 39,000 miles, approximately 60 Earth radio, and its period is 27.3 days. Its synodic period or period measured in terms of lunar phases is about 29.5 days. Newton has found the moon's inward acceleration in its orbit to be 0.0027 meter per second, the same as 1/60 of the acceleration of falling object at the surface of Earth. In Newton's theory, every least particle of matter attracts every other particle gravitationally, and on that basis he showed that the attraction of a finite body with spherical symmetry is the same as that of the whole mass at the center of the body. More generally, the attraction of any body at a sufficiently great distance is equal to that of the whole mass at the center of mass. He could thus relate the two acceleration, that of the moon and that of body falling freely on Earth, to a common interaction, a gravitational force between bodies that diminishes as the inverse square of the distance between them. Thus, if the distance between the bodies is double, the force on them is reduced to a fourth of the original. Newton saw that the gravitational force between bodies must depend on the masses of the body. Since a body of mass m experiencing a force F accelerates at a rate F/m, a force of a gravity proportional to m would be consistent with Galileo's observation that all bodies accelerate under gravity towards Earth at the same rate, a fact that Newton also tested experimentally in Newton's equation. F12 is the magnitude of gravitational force acting between masses m and m2, separated by distance r12. The force equals the product of these masses and of g, a universal constant divided by the square of the distance. The constant g is a quantity with a physical dimension, length, mass time. Its numerical value depends on the physical unit of length, mass and time used. G is discussed more fully in subsequent sections. The force acts in the direction of the line joining the two bodies, and so is represented naturally as a vector F. If R is a vector separation of the bodies, then thank you.